Alright, welcome to lesson 2.15. We're going to verify and apply the polynomial identities, including the one that we spoke about last in class. So let's go ahead and take a look. Okay, so to start off with, let's attempt to recreate the polynomial identity for Pythagorean triples. So copy the statement down, fill in the blanks accordingly, and you can test out whether you fill them in accordingly by trying out the finished statement with your choices of m and n. So we want to choose two positive integers. Remember, it doesn't make sense for the side lengths of a right triangle to be negative. And we also realize that m and n can't be equal. If they were equal, then you would have a side length of 0. And if one of them was less than the other one, you would run into a problem when you took the difference of the squares. So we stated that m had to be greater than n. And if this was the case, then the quantities m squared plus n squared, that of course represented the greatest side length, or the hypotenuse, and then the other quantities were the difference of the squares, and then twice the product, or 2 times m times n. And those are going to be the side lengths of the right triangle. And then another way of saying that is simply utilizing the Pythagorean identity to say that if we take the two smaller side lengths and square them, then that will be equal to the square of the greater side length. And so this is incredibly helpful. It now allows us to create any type of right triangle, no matter how big the sides are, how small, by choosing m and n accordingly. It also allows us to come up with Pythagorean triples really easily, whereas before, it was kind of a crapshoot. You really had no idea, whether or not your choices would work out, and then you'd have to go to the Pythagorean theorem to verify. Here we know that since this works out, we've proved it by showing, of course, that this left side is equal to this right side, that it will always work. So let's go ahead and take advantage of it to create a right triangle that meets a certain constraint. So here we want to construct a right triangle that has side lengths that are all greater than 100, and you want to show that your side lengths satisfy the Pythagorean theorem. In other words, just verify that your choices do in fact create the side lengths of a right triangle. So give this one a try on your own, and then we'll take a look at my solution. Okay, so whenever I'm dealing with a situation like this, I want to clearly write out what it is that I'm going to be creating. So I'm creating a right triangle here, and I want to represent what each side length is going to be made up of. So using the identity that we just wrote down, we're going to be writing each side length in terms of our choice of m and n. So our hypotenuse is going to be our integer m squared plus n squared. And then the other two side lengths, it really doesn't matter. They're both going to be smaller than the sum of the squares, and so we can choose to put them either place. The difference of the squares, and then twice the product of the two integers. And at this point, I then realize that my constraint is that each of these has to be greater than 100, each of these side lengths. Well, I know that if the hypotenuse is the greatest side length, I don't really need to worry about that one, because if I just make sure that the two smaller ones are greater than 100, then the bigger one will be. So I'm taking a look at the difference of the squares and twice the product, and I don't want to just start randomly guessing, because then it won't be very efficient. I want to strategically think about what would potentially make each of these other side lengths greater than 100. What are some characteristics of m and n that will ensure that? So let's start with twice the product. That means I'm going to take my integer m and n, multiply them, and then double it, which means that when I multiply m and n, I'm going to need something that's at least 50, so that when I double it, I get at least 100. Then thinking about m squared minus n squared, I know here that if this is going to end up being greater than 100, then certainly m squared has to be greater than 100, and n squared can't be very big, because if it's remotely close to being as big as m squared, then the difference of them is going to be less than 100. So what I'm getting out of this is that I'd like m to be quite a bit larger than n, so that my difference is still greater than 100, but I also need m and n to multiply to be at least 50. So if we think about just a really easy situation, let's think about a number like 25, for example, and then what would I multiply 25 by to get 50? Well, I can multiply it by 2, I can multiply it by 3. So say I take 25 and I multiply it by 2, that would give me 50. So those could be my choices for m and n, and then when I multiply it by 2, this will give me a side length of 100. But remember, I want the side length to be greater than 100. So if we choose m to be 25, then we could make n 3. And that way we'd be safely over 100 here. And then let's check the difference of the squares. If I have 25 squared, that'll give me 625, and certainly when I subtract 3 squared from it, I'm going to be well over 100. So if I choose m to be equal to 25 and n to be equal to 3, I should be in good shape. So now what I can do is actually write down what each of these side lengths is going to be equal to. Right? M squared minus n squared is going to be 625 minus 9, which is going to be 616. 2 times 25 times 3, well, 3 times 25 is 75, and then 75 times 2 is going to be 150. And then if I take the squares of each and add them together, I'm going to have 625 plus 9, which is going to be 634. So here all of my side lengths are well greater than 100, and I can go ahead and prove that this works out using the Pythagorean theorem. So I'll take the two smaller side lengths, take the sum of their squares, and certainly at this point I think mental math is out of the question for these squares of 600. So you can go ahead and compute this, and as we'll see, it'll end up being perfectly equal. And once I've go ahead and calculated the squares for each of these numbers, I can see when I take 379,456 and I add 22,500, I'm going to end up with 401,956. And so the Pythagorean theorem proves that these quantities work as the side lengths of a right triangle. I encourage you to try a couple of different options on your own, just so that you feel familiar if you haven't already, if perhaps your choices of m and n didn't work out the first time. And then let's go ahead and work on a couple of more problems on your own that we can present in class. Alright, so here are 3 for you to work on your own. First, you're going to prove that the following equation is true. Remember, when we did that in class, when we're proving that two things are equal, you can't start off by setting them equal to each other. So if you want to prove that this equals this, you've got to work with each separately and show that you can make each one look exactly like the other. So you want to split your proof into two pieces, or at least take one side at a time to show that it will look exactly like the other side. And then for 3 and 4, these are all things that we've talked about previously, so just make sure that you are thinking about that each expression makes sense, or in the case of number 4, that you're using your polynomial identity and creating your right triangle by drawing it out first and really thinking about your choices of m and n.